Hello there. Today we are talking about t-tests for groups. The first of the two varieties is a separate variances t-test. And if you've watched the last video in this series, you will realize that this formula is almost identical to the formula used for the z-test for two groups, and that the only difference comes right here in our denominator, where we are using a sample statistic, our variance of study 1, variance of study 2, or variance of sample 1, variance of sample 2, instead of the variance of population 1 and the variance of population 2. We're also using the corresponding sample sizes for those samples. Now, we're doing this because we don't always have access to our population parameters. And so just like what we did with the standard error of the mean, we're taking our sample statistics and using them as an estimate of our population parameters. Not perfect, but it is a fairly good solution. Now, since we've already essentially solved this, the only difference is where we're pulling our variances from. I'm going to go ahead and leave this unsolved. If you need to see this formula solved, go ahead and check the previous video. Now, let's move on to the pooled variances t-test. This is slightly more complex. Now, for the pooled variances test, our formula is more or less the same. It's just that we've pooled our variances. So what do we mean by that? Well, let me show you the formula first, and then I'll show you how we pool our variances. So we're taking, again, t is equal to x bar 1 minus x bar 2 minus mu 1 minus mu 2. And all of that is, again, over. But in this time, instead of using variance 1 and variance 2, we're using our sample variance, but we have a p here instead to indicate that it's been pooled, over our first sample size. Then we're adding our pooled variance over here again, over our other sample size. Now, this makes sense, and it's calculated the same as above, but what are we talking about when we mean pooled variance? Well, if we're using our separate variances t-test version, where we have n's that are the same, we have a very simple formula for calculating that. All we need to do to find our pooled variance is take variance 1 plus variance 2 and divide by 2. That's all it takes. Fairly straightforward. The issues come in when we start dealing with larger sample sizes, where we deal with unequal sample sizes, and instead of being able to divide by 2, we need to weight each variance as we put it into our sample. Let me show you how that looks. If we were to build it into our formula, we would again have x bar 1 minus x bar 2 minus mu 1 minus mu 2 over, but this time our denominator is going to be a little bit hairier. We're going to have a few more things in it, but they're not all that complicated. So at least we have that going for us. So what do we have? Well, here we're going to have sample size 1 minus 1. So again, really this is just degrees of freedom for the sample size, for the first sample size. And we're multiplying that by our first variance. Then we're going to add that to n2 minus 1. So again, degrees of freedom, but this time for the other sample. And we're multiplying that by its variance, so the variance of that sample, the second sample. Then we take that, and that is all over n1 plus n2 minus 2. And then over here to the right of this, we are going to be adding in a term that we multiply by. So we're going to have 1 over n1 plus 1 over n2. So let's take this version and move out of our conceptual area into using this with some numbers. So we had t is equal to, let's say x bar 1 was 90, and let's say x bar 2 is 87. Let's say mu 1 was 94, and mu 2 was 91. And again, I'm just making these numbers up as we go just so we have something to work through so you can see it being solved. I don't have any studies where these were the numbers. This is just an example. Then, for our denominator, we are pulling in, well, let's say that sample 1 was 30. 30 is pretty good. So let's say that we have 30 minus 1 times, let's say, variance of 15. Then we're going to add that to, let's say this one had sample size of 70. So 70 minus 1. And let's say variance was, well, typically as samples get larger, the variance goes down. So let's say this has a variance of 13. This is over 30 plus 70, so sample size 1 and sample size 2, minus 2, because there are 2 of them. And we're taking 1 over 30 plus 1 over 70 is what we're multiplying by. So let's go ahead and find green as our bordering color here. So what is this going to look like? Well, if we just start running through our numbers, we're going to end up with t is equal to 3 minus 3. See, I've already done a pretty poor job of setting this up. And that is over the square root of 29 times 15. Let's just put that in parentheses so I stay on track. Plus 69 times 13. And that is over 30 plus 70 is 100 minus 2. And then we are taking 1 over 30. We can calculate that in this step. We're going to have 1 divided by 30 is equal to 0.033. We'll just leave that as 0.033. And we're going to add that to 1 divided by 70 is equal to 0.014. Just going to keep it at 3 decimals since I did that for the first one. Now, this is going to give us an interesting result. So we're going to have t is equal to 0 over square root of, well, let's see what our numbers work out to be. We're going to have 29 times 15 is equal to 435 plus 69 times 13 is 897. All of that is over 98, and we're multiplying by 0.033 plus 0.014 gives us 0.047. And then if we move down again, we have t is equal to 0 over the square root of 435 plus 897 is equal to 1332 over 98 multiplied by 0.047. Let's move this way. T is equal to 0 over the square root of 1332 divided by 98 gives me 13.6 if we round. Now let's do that. 13.6. Whoop. We have our 0.047. And let's see if I can squeeze this in on this page. Bit of a bad habit, but I think we're far enough along in this solve that we won't get lost as we move along. So we're going to have, let's see, 13.6. Let's go ahead and find the square root. That's going to give us 0 over 0.3, or rather, sorry, 0 over 3.69 times 0.047. And if we take our 3.69 times 0.047, we get 0 over 0.17, and 0 divided by 0.17 gives us 0, a terrible result. If we were, however, to say that perhaps this instead was 91, let's say we do some revisionist history here and say that instead we had 91 up here, which would give us 4, and so this would end up being 1 divided by 0.17 gives us a t score of 5.88. So, poor example, but the math holds up. Hopefully this is useful for you. There are not a whole lot of times when you would hand calculate this, but it is helpful to know for class, especially this area here where you're weighting your each variance. That actually comes in pretty handy as to knowing how you do that, and so you can just do that on the fly and use it in your head as sort of make quick judgments about the data before you go to all the time of running all the statistics, just so you have an idea of what things are going to look like once you actually get to running the statistics. I know I've had some professors who like to get early information from the data before they go through and they run everything. So if we just have one thing and we start running the analysis on that before we continue with the rest of it, so we start to see what the data looks like. I guess it's mostly just because we've already gone through so much hard work. It's fun to start to see what sort of results we've found in the data. And that really is one of the greatest parts of being a researcher. Hopefully this is useful for you. If it has been, let me know down below. I'd be encouraged to hear it. And until next time, cheers.